Okay.
Okay. Good morning. Good morning. This is the class 3. I will go through the previous 2 classes. Whatever the things we have discussed, just I will summarize for a few minutes. I will summarize it for a few minutes. Because now already I have handled 2 hours. This is the 3rd hour I am handling. Now I will summarize the previous 2 classes, whatever the things we have discussed. Now force, we have discussed about it. Force is an action which moves the body or stop the body. The force is an action which tends to move the body or restrict the motion. The characteristics of force. The characteristics of force are one is magnitude, the size, amount of the force applied, the direction along which the either upward or downward direction, and the line of action, and point of application where the force is acting. Then we have discussed about the resolution of forces. Resolution, the vertical component, horizontal component, and horizontal component and vertical component. We have discussed about these things. Resolution of forces, and again we have discussed about the composition of forces. In composition of forces, now we have first there are 4 steps. One is resolving the forces into horizontal and vertical components, then summing up them, the sum of the vertical components and sum of the horizontal components, then taking those sigma V and sigma H. Now we are calculating the resultant of the force. We have discussed about this, and we have also discussed the stress. Stress is an internal resistance set up in the material against the external load. Now this we have discussed about this. Now in this again there are tensile stress, then compressive stress. Now tensile stress is the stress induced against the tensile force. When we apply the load, the body gets elongated. The stress induced in the material is a tensile stress. Then similarly, when you apply the force, when the material gets reduced, its length gets reduced, the force applied is a compressive force, and the stress induced in the material is a compressive stress against the compressive force. Then we have discussed about the Hooke's law. Now Hooke's law, now elasticity, elastic limit, and plasticity. Now elasticity is the property of the material by virtue of which the body regains its original position after removal of the external force. Now this will be up to certain limit. Now the body comes back to its original position after removing the external force. Now this property is called elastic property of the material. Now this holds up to certain limit. up to certain limit. After that limit, the body will not come back, returns back. It gets into plastic state. That is the collapse or the fracture. The body gets into the plastic state. That means the body will not come back. It is a permanent deformation of the material. Now, therefore, elasticity is the property of the material by virtue of which the body regains its original position, original shape. And now this property is called elasticity, and this happens to a particular limit within the elastic limit. That is elastic limit. Beyond that, the body will not come back, and it will go to the permanent deformation. That is, the body gets into plasticity, permanent deformation. And we also we have discussed about the tensile test on steel, that is specimen, compressive load, how to calculate the stress and strain. We have discussed about this, and also we have discussed about the stress strain diagram for the ductile material, that is steel, MS material. We have discussed about the working stress, yield stress, ultimate stress, then failure stress. Also, we have discussed about the Young's modulus. Young's modulus, now it is the property of the material. It is the elastic constant. This is called elastic constant of the material. Now this is the ratio between the stress and strain within the elastic limit. Now that is Young's modulus. It is a elastic constant. It is elastic constant, and it is calculated. The stress is calculated now based on the load applied and the area, cross-sectional area of the material element, and strain is calculated based on the deformation, that is change in length over the original divided by the original length of the material. The Young's modulus it is defined as the stress upon strain. It is the ratio between the stress and strain. It is a material constant within the elastic limit. This is the elastic limit. And we have discussed few problems. That is the stress strain. If you know these things, definitely we can solve many number of problems. Now we have discussed about 3-4 problems. Now, is there any query? You can call me back later after the presentations. And our students are not much familiar with the dimensions or cross sections of the material, sections. Sometimes our students will get confused with the circular, square. While calculating the area, they will go mistake. Please take care of this area calculation of cross-sectional area. And again, sometimes they are not able to understand the cross-sectional area of a hollow section, that is external diameter, internal diameter, and they will sometimes mistake that. They will mistake the calculation of area, that is pi by 4, pi d square by 4. While deducting, so there are so many mistakes taking place. Now I request the students to go through this and kindly make a perfect attempt. And these are the 4 problems we have solved. Now there are many problems. Many problems are available in the textbooks and also in the question papers. Now I request you to go through those problems, solve them, and get ready for the examination point of view also, and also from the future life of our engineering life. Now today I will discuss about the shear stress. Now the shear stress. Now shear force. Now let us understand the sections. There are 2 sections. See, in a material, the material section, there are number of sections. In a beam, if you take, there are number of sections. Now those sections, they will rest. They are comfortable. The beam is comfortable in resisting the force. Now what is happening? Is there any difference in the load between the sections? Then the material will slide. Now here it is clearly shows that the deformation. See, this is the shear force acting on the surface. There is the surface material shear force is acting on the surface. Now here, now if these two are unbalanced, when these two are unbalanced, so what is going to happen? The body will deform. The body will deform. Like it is in the design, it is assumed it is designed. The beam is made of number of sections. Beam is made of number of sections. The beam is made of number of sections. All the sections are resisting. One is in the opposite upward. The other force is shear force is acting the downward. So therefore, these two are balancing. When these two upward force, shear force, and downward shear force are equal, the beam is comfortable in resisting the force. Whereas if there is unbalance in the force, definitely there is a movement, there is a shearing. This force is called the force which causes the shear in the beam section or any element, load resisting element. That is the shear. We are calling this as shear force, and the corresponding stress is called shear stress. Now the shear stress. See, for example, this is the force, the shear force, and this is the area. This is the shearing area. Therefore, the stress induced. Now we have to design the elements in such a way that this should not happen. The deformation should not happen. Now, therefore, now the stress, we have to create the section in such a way that design the element in such a way that it should not deform, and we have to design in the opposite direction. We have to provide the section to resist the shear force. Now, therefore, the shear force divided by the shear force divided by the shearing area gives you the shear stress. The shear stress. Now, this is one of the most important cases one should address here. Now, both mechanical engineers and also civil engineers should take care of this. And then, now this is how we will define the shear stress. Shear stress is defined as the shear tangential force, that is the force applied. That is, it is shearing force. The force applied. It is the shearing force. It is the shearing force. Now this force divided by the area, the shearing area. Now that is the shear stress. Shear stress is tangential force divided by the sliding area. That is the shear stress. Again, it is also in the Newton per millimeter square. That is force by area. And similarly, the shear strain. The shear strain is deformation. The shear deformation. The amount of deformation divided by its original length. Now that gives you the shear strain. Now similarly, there is another constant called the shear modulus. Now earlier we have discussed about the Young's modulus. Young's modulus is direct loading. Young's modulus is direct loading. Now direct loading. Young's modulus is direct loading against the main against the direct force. Now whereas here the shear modulus, it is another constant. It is shear modulus, or sometimes we will call this as rigidity modulus. Shear modulus or rigidity modulus. Now it is abbreviated. Now some textbooks people it is seen as C. In some textbook it is N. Now some people are talking in terms of C or talking in terms of N. Therefore, shear modulus is the ratio between shear stress to shear strain. It is also again in the Newton per millimeter square. Now, it is another elastic constant within the elastic limit. Now, this is more good up to elastic limit. Beyond that, no, this is not this modulus or the constant. It is not up to the elastic limit. It is constant. It is also an elastic constant. I think now we have discussed about the two elastic constants. Number one is Young's modulus and number two is shear modulus. Then further, now there is one problem. We will discuss about this problem. Now our students should understand very carefully that is how to solve these problems. Now I will solve this problem. Now first read the problem very carefully. Our students are lacking in understanding the problem and conversion and calculation. There is much more problem. And I request our students to address these problems. Now, the ultimate shear stress of a made steel plate is 400 newtons per millimeter square. Calculate the diameter of the hole which can be punched through it without exceeding a compressive stress of 8 tons per centimeter square. Now, this is the where the conversion plays a very big role. Now, please go through the conversion, how to convert this into newtons per millimeter square. Now, I request all the students to apply the same unit throughout the problem. And the thickness of the plate is being 12.5 millimeter, and also determine the strain in the punch. The Young's modulus of the material is 2 into 10 to the power of 5 newtons per millimeter square. This is the problem. Now, first write down the given data. Ultimate shear stress, that is the stress induced in the material while applying the shear force. The compressive stress, that is the direct force. Is it not? Now, let us assume. Now, please understand, there is a plate. There is a plate. There is a metal plate. So they have given the problem like this. There is a metal plate. Metal plate having thickness. Thickness of the plate is 12.5 millimeter. This is the 12.5 millimeter. So this is 12.5 millimeter. 12.5. 12.5 millimeter. And there is a hole. The hole has to be punched. Well, let us have. Well, now to make a hole of this plate, what is the load required? That is our problem. First, understand the problem very carefully. Now, then only you can solve the problem. First, write down all these data, given data, and find out what is to be done. They have asked thickness of the plate being. They have asked calculate the diameter of the hole which can be punched. Isn't that? Calculate the diameter of the hole. What should be the diameter with this stress? So this is compressive stress, and also they are given the ultimate stress, shear stress and compressive stress they are given, and also they are given the Young's modulus. So we need to calculate the strain in the material, and also the load, and also the diameter. Now, usually this will be asked in this kind of problem will be asked in the examination for 10 marks. So therefore, now please note how to calculate it. First, now don't forget the original equations. That is original definitions. Shear stress, shear force divided by sliding area. Now here there is a problem with our students. Now there is a problem. There is a problem with our students. So see, this is the area. This is the hole. Now this is how the thickness. This is the thickness. Our students don't understand how to calculate that is shearing area. Now there is a hole. So in that hole, the area is how to calculate the area of this shearing. The shearing space. This is the shearing area inside that is hole. Now this is now the problem is here. What is the shearing area? Now suppose if you open that, now the circular hole is like this. Now if you open this, now this is the area. Now this is the area, circular hole. The circular hole. If you open this, now this is the tangential area. Isn't it? How to calculate this? This is the big problem. That is now how to calculate this? The calculation of calculating this area, it is that is circumferential length. That is pi into d. Pi into d is the circumferential length. Isn't it? Pi into d, pi d, and the thickness is t. Now the triangle is equal to t. T. Therefore, area is equal to. We need two dimensions to calculate the area. The one is the length, the other one is the depth. Isn't it? Length, breadth. Now therefore, this is how we have to. Now this is what you have written here. This is the area. The area of the that is area of the hole. That is inside shearing area. Shearing area of the hole. This is the shearing force applied, and this is given. They have given this. Shear stress given. It is 400 newtons per millimeter square. Now apply this, and there are two unknowns here. P we need to find out, D also we need to find out. But we know the definition. How to calculate, what is the definition? The shear stress definition. Shear force divided by sliding area. And then after doing, see, there are two definitions, there are two unknowns, and there are two unknowns, we have one equation. Therefore, let us keep pending for a while. Then next we will go to, let us calculate the compressive stress. Compressive stress means that is direct loading, load application. Apply the force, then divided by load divided by cross-sectional area. Cross-sectional area is, there is a confusion here. Area, this is shearing area, the other one is cross-sectional area. Cross-sectional area is pi d square by 4. Now this is how we have to calculate the shear force, shear compressive force. Shear, this is the shear stress and this is the compressive stress. Make difference between these two. Shearing area is the area, the surface where through which the punch is, the hole is made. That is inside the circle. That is the area. Now here cross-sectional area is directly. That is the area of that hole. That is pi d square by 4. Isn't it? Now therefore, this is the equation number 2. This is the equation number 1. This is the equation number 2. Here also we don't know the load and we don't know the diameter. Now therefore, what we should do? Next, what we should do? Now from equation 1. Now from equation 1, P is equal to this is how you have to one. And also I request. I want to highlight something here. Our students they are doing mistakes in transferring this. Isn't it? Cross multiplication. Now this will go. Now see. Now P is equal to this pi d square by 4. 4 should go to the, isn't it? And to the upward. Then see, and this will remain in the denominator. Now therefore 4P into, again this 4 will come down. Now that is cross multiplication. There are many mistakes committed by our students. Now please learn these things. And from this, now we have calculated the from equation 1, P is equal to this one. In terms of D, we have done this. Isn't it? But this we got it. Then in equation 2, substitute the value of P. Substitute the value of P. Then D is, we can calculate the D. Now D can be calculated. Now when you substitute the value of P into the equation 2, then we can calculate the diameter of the hole. Now again go back and substitute the diameter, then we will get the total load. Then one problem is solved. Our one problem is solved because two problems we have solved. One is diameter is calculated, the other one is load we have calculated. Two things we have done it. Then similarly, then after that, now we know that this is the original equation. That is Young's modulus is equal to load divided, stress divided by strain. Young's modulus is equal to stress divided by strain. Now therefore you just make a change, that is just transfer one term to the other side. Then strain is equal to load that is stress we are given and Young's modulus is given. Now therefore we can calculate this is the strain in the material. Isn't it? Then our problem is solved. Isn't it? Now further, now this is how there are so many problems available in. There are many problems available in the textbook. There are so many textbooks available in the market, and also you have your faculty members. Please discuss with them and follow their instruction and go to the textbook, and solve many more problems. If you want to solve one more problem, you can send that problem in our mail and mail ID tomorrow. In the next class, I can solve those problems. I can give the solutions for this problem. Then in stress and simple stress and strain, now we'll go to the next. That is the next part of the simple stress strain. The another important issue to be addressed by the engineers. Now in construction industry, in construction of equipment or structures, whatever may be. See, we may come across with these sections like, this is the section 1. The bars of varying cross section. Now this is one section, this is another section, this is another section. There are 3 sections. Sometimes many more sections. Now we have only 3. Sometimes we may have a little more, isn't it? Or little only 2. The bars are varying cross sections. Bars are varying cross sections, isn't it? Now therefore bars are varying cross section. Now let us assume that the length is section 1, section 2, section 3, and here this is year 1, year 2. That is the length of the material, length of the section 1, length of the section 2, then length of the section 3. Isn't it? Now, sometimes the material may be different. Isn't it? We have different materials maybe. The one is steel, the other one is copper, the other one is aluminum, or sometimes all are same material. All the three parts are made up of same material, sometimes different materials. When it is made out of same material, so section 1, section 3, now when it is made out of same material, then what happens? The Young's modulus of the material remains same. Isn't that? Now when Young's modulus of if the material is made out of same material, then Young's modulus of the material will be same for all the 3 sections. Isn't that? The length, we know that is L1, L2, L3, and cross-sectional area is also different. No, isn't that? Length different and cross-sectional area different for all the 3 sections. But if the material is made out of, same material, then Young's modulus remains same. If the material is made out of different material, then the Young's modulus of the material will be different. Then what is the? It is Young's modulus of the section 1 is E1, Young's modulus of the section 2 is E2, Young's modulus of the section 3 is E3, etc., etc. And we know that. Then how to analyze this? How to solve the problem? Now, when you apply the force, the body gets elongated. Now it is elongated by how much? Now, total deformation is delta L. Isn't it? Total deformation is delta L. Isn't it? But whereas delta L of this material, this section, delta L of this, delta L means it is change in length, isn't it? Total change in length is equal to delta L, change in length of the bars of varying cross section bar. Now delta L1 is the change in section 1, length of change in section. Delta L2 is the change in length of the section 2. Delta 3 is the change in cross section of the change in this part, isn't it? There is change in material, change in material delta 1, change in material delta 2, change in length of the material, that is delta 3. So therefore, now total change in length is equal to delta L. Then delta L1 is equal to R. Delta L is equal to R. Delta L1 plus delta L2 plus delta L3. Isn't it? Now delta L1 plus delta L2 plus delta L3 plus if you have many more, we can add any number. Now this is what we have written here. Here the load applied for all the 3, that is combined section. Now when load applied is P. Now we know that the original calculation, changing delta, calculating the change in length of the material. When the load is applied, delta L is equal to PL divided by AE. Already we have discussed about in the previous class. Delta L is equal to PL divided by AE. Isn't that? Now therefore PL by AE. Now P is common, we have taken out. Therefore length is different, L1. Material is different, E1. Cross section area is different, A1. Plus this is again L2, length is different, material is different, E2. Then material is cross section area is different, it is A2 plus L3, like we can substitute this, isn't it? Now then our problem is solved. We have solved our problem. Our problem is solved. Now this is what I have discussed. Now here, now that is what I have explained now. Delta L is equal to, that is a total change in the bar. Total change in the bar. Delta L1, the first part, delta L2, second part, and this is the third part. Now we know that delta, that is delta L is equal to PL by AE. Therefore it is delta L1 is equal to P L1 A1 E1. Isn't it? Delta L is equal to substitute all these things. Now in this problem, in this equation, it is assumed that all the E, that is material made out of same, isn't it? Same material, isn't it? All the three sections are made out of same material, and the load applied is all common. The different only change in this is that is L1 is different, cross section area is different, isn't it? Now then we will take out this P and E outside. Therefore, length divided by A1, length divided by A2, length divided by A3, plus if you have many more, we can do that, isn't it? Now similarly, see, now I have taken one example. Now again I request our students to go, that is, read very carefully the problem. Unless you read the problem very carefully and without understanding the problem, it is very difficult to solve the problem. First read. Now, therefore, now see, there are, in this problem it is given. Now there is a figure here, diagram is given. See, the length of the first is made out of aluminum and the second one is made out of steel, isn't it? This is 380 millimeter and 300 millimeter. Now it is subject to a compressive force P, isn't it? Compressive force P, due to this compressive force, there is some change in the deformation. Total deformation is 0.25 millimeter. And in the problem it is given that A1 is given. A1 is area of the cross section. Area. Now sometimes we will call this. Some people will say it is section 1 or section aluminum section, steel section, whatever may be. Now this is aluminum section. Some textbook can see A suffix AL aluminum. A suffix it is steel AS. Now in different textbook, different people, different way they speak. Isn't it? Whatever they speak, the concept is this. Now different cross section, varying cross section, that is aluminum and steel. The area is given here. It is area is 10,000 millimeter square, and also the steel cross section area is given. It is 2,500 millimeter square. The load, now we need to calculate the application of load. What is the load? Isn't it? Now they asked too many questions here. A member is formed by connecting a steel bar to an aluminum bar, as shown in the figure. Find the magnitude of the force which caused the total length of member decreased by 0.25 millimeter. It is decreased by 0.25 millimeter. The values of elastic modulus for steel and the aluminum are given. 2,100 tons per centimeter square. Centimeter square is missing here, and 700 tons per centimeter square. Calculate also the work done by the force. This is our problem. Now normally this will be asked for in the examination for 10 marks. You know the rate of the given data, that is Young's model. Now after converting this straight away, I have written here. Now 2.1 into 10 to the power of 5 newtons per millimeter square, and aluminium it is 0.7 into 10 to the power of 5 newtons, and these are the given data given. So from this data, now let us calculate the requirement. Then there are two sections. Only we have two sections. Delta L. Delta L is equal to delta L1 plus delta L2. Delta L1 plus delta L2. So here P is common. Length of both the members are different, and area is also different. Young's modulus is also different. So we know that it is given. Please substitute here. It is 0.25 millimeters is equal to P. Now substitute all that. Now this is substituted in centimeter. So therefore, now calculate this, and the only P is unknown here. The P, when P is unknown, therefore P is equal to 220 kilonewton. That is the load. Isn't it? They have asked this. They have asked what is the magnitude of the load to cause so much deformation. Now see, after that, now one more question they are in the exam, in the question asked, work done. Work done is equal to, we know that the load multiplied by deformation. Isn't it? Load multiplied by deformation, that is average loading. Therefore, half multiplied by load applied multiplied by deformation. Now this is the value of work done. Work done, that is Newton millimeter. Isn't it? Now I request I suggest our students to follow the same units throughout the problem in your subject. And the next, many more problems are here in the year also. There are many more problems are available in the textbooks and also in the test papers. Please try to solve few more problems. Then we'll go to the next issue of this stress strain. The most important aspect in that in stress and strain. Now this chapter, now one should understand the lateral. Till now we are discussing only about the strain. Now here afterwards we have to discuss the strain in the lateral direction also. See, for example, now this is the linear dimension, that is rubber. This is the linear dimension, and this is the lateral dimension. Lateral dimension is diameter. Now whereas here, this is the linear dimension along which the load is applied, and these two are the lateral dimension. The lateral means perpendicular to linear. Lateral in the cross direction. Transverse direction. The linear direction and transverse direction. Now this cube is made out of, that is length, breadth, and width. There are three dimensions. This is linear, and the other two, the application of load is in this direction. Therefore, it is linear direction. The other two directions are lateral direction. Now, therefore, similarly, one more example is given. When we apply the force in the linear direction, what happens in the lateral dimension? When you apply the force, when you apply the linear, then the diameter of the bar gets reduced. The diameter of the bar gets reduced. Now, whereas if you apply the compulsive force, the diameter of the bar increases. Now, therefore, lateral change. Now, so far we are discussing only about the strain. Now, here afterwards we must say linear strain and lateral strain. Linear strain and lateral strain. Most important. So, see linear strain and lateral strain. Linear dimension and lateral dimension. Now, this is the circular section and this is the rectangular square section. Now, whatever may be, please understand. Now, this is the linear and this is lateral dimension. Linear dimension and lateral dimension. When you apply the force, tensile force, length increases, lateral dimension decreases. When you apply the compressive force, lateral dimension decreases, lateral length decreases, and the diameter increases. And see, with this, now we can study lateral strain and Poisson's ratio. Lateral strain and Poisson's ratio. Now, before loading, this is after loading. That is, now this is after loading. This is also after. One is linear. When we tensile force, the other one is compressive force. Now here, one should understand the linear. See, now we know that strain is equal to change in length divided by original length. It is not. It is the change in length per unit length. It is not change in length per unit length. Yes. Now similarly, linear strain. How do you define the linear strain? Linear strain is defined as change in length divided by original length. Similarly, lateral strain is equal to lateral strain. Change in lateral dimension. Change in lateral dimension divided by original lateral dimension. Whether it increase or decrease, isn't that? There is strain, lateral strain in the lateral direction. Now, similarly, see here the linear strain, isn't that? Change in length divided by original length. Now, whereas here in the lateral is the lateral dimension, change in lateral dimension divided by original lateral dimension. Change in lateral dimension divided by original dimension. I think one should understand this very clearly, isn't it? There is a confusion here always. Our students gets confusing always with this. They are not able to understand which is linear and which is lateral, isn't it? Therefore, I request our students, I suggest our students to understand all these concepts, basic concepts, isn't it? Then further, if you proceed, now, if you proceed further, now continuation of that, see lateral strain and Poisson's ratio, say we have written here. Now the same thing what I have explained, the same thing is printed here. Lateral strain is equal to change in lateral dimension divided by original lateral dimension. Change in lateral dimension divided by original lateral dimension. Isn't it? And linear strain, change in length divided by original length. Isn't it? The another one constant, it is also again material constant. It is Poisson's ratio, isn't it? Poisson's ratio. Poisson's ratio is the ratio between change. It is the ratio between lateral strain to linear strain. It is again material constant. So please remember. Now already we have discussed the constant. That is number one is Young's modulus. It is the ratio between stress and strain within the elastic limit. It is a material constant. The second one is, it is a shear modulus. That is again the shear stress divided by shear strain within the elastic limit. Within the elastic limit. And the third one, it is Poisson's ratio. That is again elastic constant. That is also the material constant. It is also, it defines the material constant. There is the ratio between lateral strain to linear strain. Some people avoid this lateral Poisson's ratio as 1 by m. Isn't it? 1 by m. Now some people will say mu. Isn't it? Depending upon their convenience, the people are using this. That is lateral strain divided by linear strain. Now this should become E. There is a wrong here. Please make the correction this. Now this is lateral strain divided by linear strain, isn't it? Linear strain. Now therefore lateral strain, how to calculate the lateral strain? The lateral strain, no, it is a material constant. Now for a given material we cannot change the Poisson's ratio. For a given material, the Poisson's ratio is a constant value. Isn't it? We cannot change it. Isn't it? For material to material it is different. Isn't it? Therefore we are not able to change that. Now for a given material it is a constant value. No, it is 1 by m. That is. So, therefore, lateral strain is put. We can calculate the linear strain. Linear strain can be calculated. Measure the deformation, change in length. Divided by original, that gives us the linear strain. Isn't it? Then this is the material constant. Now, when you know the material constant and the linear strain, we can easily calculate what is the lateral strain. Very simple. We can calculate the. Then similarly, further if you go, see, this is how we can calculate. This is the Poisson's ratio. Lateral strain divided by linear strain is a constant. It is a material constant. So this is a constant for Poisson's ratio. So it is again a material constant. That is 1 by m, or somebody will call, somebody say it is mu. Both are same. Isn't it? Then again, when we apply the force, when we apply the load, when we apply the force, it is understood very clearly that there is a change in linear dimension, there is a change in lateral dimension, and there is a change in lateral dimension. There is a change in linear dimension, there is a change in lateral dimension. It is clear. Now, it is understood that now this material has some volume, isn't it? Length, breadth, and depth, isn't it? It has 3 dimensions, isn't it? When you multiply these 3, you will get the volume, isn't it? Now, definitely there will be a change in volume. Definitely there will be a change in volume, isn't it? Because we apply the force. When you apply the force, now definitely there will be some small change in the material, isn't it? Volume of the material. So therefore, now see volumetric strain, isn't it? Volumetric strain. The similar way, is the volumetric strain. Change in volumetric strain, it is change in volume divided by original volume. Change in volume divided by original volume. Change in volume, and this is delta V, small v, delta. Change in volume, a little change. This is the original volume of the material. And therefore, change in volume is equal to VV. Now this is no, this is arrived based on so this is arrived from this no, see here the length delta L, change in length, the change in dimension, lateral dimension, that is delta V, change in lateral D, isn't it? Now there were three changes. One is delta D, delta L, and delta V. Breadth, width, and length. Delta L, delta V, delta D. There are three dimensions, change in dimension. Now see, now here one thing we should observe, one thing we have to, I would like to highlight here. See here, the length increases. Whereas in this case, the length increases. Length increases, whereas the lateral dimension gets decreased. Therefore, one is positive, the other two are negative. The other two are negative. One is positive, the other two are negative. Therefore, we have arrived. Now this equation arrived from the isn't it? So arrived from this. Therefore, change in volume can be calculated using this equation. From this we can calculate the change in volume. Isn't it? If you want to learn a little more about this, now please concentrate and ask your faculty members and also go through the textbook. Now at this point of time, I think not much description or understanding much more. I think for our student level, maybe not very required. Now again, in the lateral strain and lateral strain and Poisson's ratio, lateral strain and Poisson's ratio, we have let us solve one problem. So, to solve this problem, lateral strain and to solve the problem. This is let us take one example. Now, a copper wire 2 meter long, 20 mm in dia is subjected to a pull of 45 kilonewtons. Subjected to a pull of 45 kilonewtons. Find change in length and dia of the wire. If given Young's modulus is equal to 1 into 10 to the power of 5 newtons per millimeter square and m is equal to 4. Now here, m is equal to 4. Now please understand, please remove this. Now there is some wrong data entered here. Now how to calculate this? Now already I told you that you should read the problem very carefully. The given data should be very carefully studied. Now therefore, copper wire 2 meter long, 20 mm in dia is subjected to a pull of 48 kilonewtons. Find the change in length and diameter of the wire is given that is Young's modulus of the material is copper wire is 1 into 10 to the power 5 newtons per millimeter square and m is equal to 4. Now write down the given data. Now therefore, now here m is given as 1 by m. 1 by m is equal to 0.25. 1 by m is 0.25. 1 by n is it is 0.25. 0.25 it is the Poisson's ratio. Now we need to calculate the change in length delta L and delta D. We need to calculate the change in length and diameter. Now therefore what we should do, now we must now from the given data please write down, that is area is given, diameter is given, then area calculate from the given diameter. It is apply the regular equation, find equal by 4 and stress is equal to load divided by cross-sectional area. And from the original equation, from the original statement, that is linear strain is equal to, we know that Young's modulus is equal to stress divided by strain. From there we can calculate the linear strain. Linear strain is equal to stress upon Young's modulus. And lateral strain is equal to, because they have given this m, when 1 by m multiplied by, this should be E. There is some error. Please request to make a correction. That is, it is the linear strain. This is linear strain. 1 by M multiplied by linear strain is equal to 0.2. Then this gives you the lateral strain. Yes or not? Therefore, change in length. Change in length is equal to, we know from the original statement. That is, linear strain is equal to change in length, linear strain is equal to, now from the original statement, that is strain is equal to strain is equal to that is change in length, change in length divided by original length. From this original length. And therefore you transfer this, that is the linear strain. This is the linear strain. Linear delta L can be calculated. That is just transferring this. Now we can calculate the change in length. Now similarly, from the lateral strain, we have calculated the lateral strain. We have the lateral strain here. We have the lateral strain. We have the result, lateral strain rule. Now therefore, from this lateral strain, now delta from the lateral strain, now this is the change in linear dimension, change in length delta L, and from the lateral strain, substitute this, that is lateral strain is equal to, we know that the lateral strain is equal to lateral strain is equal to lateral strain is equal to, you know that lateral strain is equal to delta D divided by D original. Therefore, change in length delta D is equal to lateral strain multiplied by original dimension D. Therefore, if we have both the values, now lateral strain you have calculated here, this lateral strain multiplied by the diameter they have given. Now substitute this, you will get the value of the diameter. Then our problem is solved. So there are two problems. Now our problem is solved. They are asked to calculate what is the change in length and what is the change in diameter. Very simple problem. Don't forget the stress strain and Young's modulus and all those things. Now, one more problem. The other problem we have taken, it is the other in the reverse direction. A mild steel bar 28 mm in dia was subjected to an axial pull of 60 kN. The measured extension for a gauge length of 200 mm was 0.09 mm and change in dia was 0.00375 mm. Calculate the Poisson's ratio, Young's modulus, and shear modulus. Isn't it? Now, therefore, please read the problem very carefully and write down all the given data. These are the given data. Diameter of the bar is 28 mm. Length of the, here one should understand here what is the gauge length. The gauge length. Now, in the first class, I have explained about this. The gauge length, that is, in the test specimen, we are marking 200 mm normally in the laboratory. Isn't it? The 200 mm. For example, this is the test piece. We will mark the 200 mm. Now, this length is called gauge length. In this gauge length, in the laboratory, they have measured the extension, measured extension, change in length, delta L is in 200 meter gauge length. They have measured the change in length, that is the extension, is 0.09 meter. Now, you collect all the information, collect the data. And also they have measured the change in diameter. If the change in diameter is, now they have asked to calculate what is the Poisson's ratio, Young's modulus, and the shear modulus. So these are the three questions they have asked, three data, they have asked three information we need to calculate from this problem. Now in this problem, now please understand, don't forget the stress, load divided by cross sectional area, strain, change in length divided by original length, lateral strain, change in lateral dimension to the original lateral dimension. Young's modulus is equal to Young's modulus is stress upon strain, isn't it? Don't forget all this thing. And lateral and Poisson's ratio is equal to lateral strain divided by linear strain. Don't forget all these things. Now this is the overall we have discussed till now, isn't it? So therefore the solution we have, it is like this. No, change in diameter, isn't it? Now change in dia given delta D is equal to change in diameter. They are given change in diameter. See, now lateral strain is equal to they are given change in diameter 0.00375 and 28 millimeter. So therefore lateral strain is equal to this, isn't it? Now similarly linear strain is equal to, that is delta L divided by, they have given the data is given here in the problem. Therefore this is the lateral strain and linear strain. Isn't it? So therefore the lateral strain and linear strain. So from when we have calculated these two data, from this data, now we can calculate the Poisson's ratio. Isn't it? We know the definition of the Poisson's ratio. The Poisson's ratio definition is lateral strain upon the linear strain. Isn't it? From this we can calculate. Now this is the value of Poisson's ratio. This is the value of Poisson's ratio, isn't it? And further, if you move, we know that from the fundamentals, we know that stress is equal to load divided by cross sectional area. Isn't it? Calculate the area. Load divided by cross sectional area. Isn't it? So this gives you the information, that is stress. And from when we know the linear strain and stress, from there we can calculate the Young's modulus. Young's modulus is stress upon strain, and that will give you the information, isn't it? Now therefore E is equal to 2.16 to the power by Newton sum. And you know, this is one relation between the Young's modulus and shear modulus. There in the next class we have one more relationship between the elastic constants. I will discuss about those things in the next class. Now for the time being, let us know that is the relationship existing between the Young's modulus and shear modulus. Young's modulus and shear modulus. Now from this directly we can submit all the given data. Now that gives you the shear modulus. Then our problem is solved. They have asked to calculate the Poisson's ratio. Now Poisson's ratio we have calculated. They have calculated the Poisson's ratio. Poisson's ratio is this one, isn't it? And the other data is other two data they have asked to calculate. That is the Young's modulus. Young's modulus is 2.1. This is and shear modulus. Now these are the given data, isn't it? And you can solve many more problems. No, but don't forget between the fundamentals. No, the stress, strain, Young's modulus, linear strain, lateral strain, Poisson's ratio, shear modulus, shear. No, we will play with only these things. If you understand these things, no, definitely it is possible you can score much more. No, more. It will give you value for your examination point of view also, from your life, engineering life point of view also. We can enjoy the subject and we can do the best, isn't it? So this is how I will come across. Now the other one is compound bars. Now let me discuss these compound bars and the rest in the next class. That is on Thursday, isn't it? Now Thursday I will take up this. We will discuss about this compound bars. Now the compound bar means combination of two or more materials. Combination load resisting element combining two or more material, isn't it? For example, the best example is, that is one is our RCC column is the best example. RCC column is one best example. The RCC column is made out of two materials. One is the steel, the other one is concrete, isn't it? Best example for composite part. And similarly, in encasing steel with aluminum or a copper tube, that is another example for the composite bars or compound bars, isn't it? They are again load resisting elements. How they behave, isn't it? How they behave. Now we have to understand how they behave against the force. How to calculate, how to differentiate between the materials. What material, which material will, how much load it will receive, isn't it? Because all the materials are not same. Ink modulus is different from the different material. They are combined together, and how they behave. What is the stress induced in the different material? For example, if you take the column, in the column steel behavior is different, and RCC, that is concrete behavior is different, but both are doing the same job. Both are put together, how they behave, and what is the stress induced in the steel, and what is the stress induced, what is the amount of stress induced in the concrete, like for different combinations. We will study this in the next class, isn't it? That will be on Thursday, isn't it? Thank you very much for hearing for a long time. Thank you so much. We will discuss further. We will continue in the next class. Thank you very much. Thank you. Srinivas.